Today we are going to see a very important concept of electrostatics. I have written that concept in the form of a question, and the question is, can we define volume charge density due to a point charge? You have definitely an idea of volume charge density. The volume charge density, which is usually denoted by the symbol rho, is defined by charge divided by volume. It means we consider the charge distributed in a particular volume. Let us say V is this volume and Q is the charge distributed in this volume. Then we define the volume charge density as Q divided by V. Okay, charge divided by volume. So the student generally think that when we talk about a point charge Q, then the volume charge density at the position of the point charge will be again Q by V. But since point charge occupies no volume according to the mathematics, because in mathematics a point has no dimension, it is dimensionless, its volume is zero. So people generally think that when we will define the volume charge density for a point charge, that will be Q divided by 0, because according to mathematician the volume occupied by a point charge will be 0, and so this will be infinity, that is undefined. So in the view of mathematician, the volume charge density of a point charge must be undefined. But the real situation is not so that. Okay, we can, in real practice, we can define the volume charge density. But how we can define the volume charge density due to a point charge, we will learn it. Actually, every charge distribution are volume charge distribution. But how you can say that every charge distribution is volume charge distribution? Because any charge distribution must occupy some volume. That volume may be very small, but never zero. So we can approximate any charge distribution to a volume charge distribution. It may be discrete, it may be a line charge distribution, it may be a surface charge distribution. But all these charge distribution, even you can consider a point charge Q, this will also occupy some volume. If the charge distribution is discrete, as you can see in this second figure, this will also occupy some volume. If the charge is distributed on this line, then strictly volume is not zero. There will be some volume, there will be some width in this line distribution too. And similarly, if the charge distribution is a surface charge distribution, we cannot say that this distribution does not occupy any volume, but there will be definitely some volume. Okay, so every charge distribution can be approximated to be a volume charge distribution. Okay, but depending on the geometry, sometimes we approximate the charges to be a point charge, a line charge, or a surface charge. Okay, so we can define the volume charge distribution for any charge distribution. Volume charge density we can define for any charge distribution, that may be even a point charge or a discrete point charge distribution or a line charge or a surface charge. For any charge distribution, we can define the volume charge density. Don't think that in case of point charge or discrete charge distribution we cannot define volume charge density. We cannot define volume charge density in case of line charge or surface charge. But in any charge distribution, I am saying you that we can define the volume charge density. But how? Actually, Dirac Delta function is the suitable candidate in terms of which we can express or we can define the the volume charge density in terms of Dirac delta function. So I have written here in terms of Dirac delta function, any charge distribution can be expressed as a volume charge distribution, and once you are able to express any charge distribution in terms of volume charge distribution, it is possible that we can define the volume charge density. Okay. So Dirac delta function is the suitable candidate to express any charge distribution, that is even the point charge, discrete charge distribution, line charge or surface charge distribution. Any charge distribution can be expressed as a volume charge distribution in terms of Dirac delta function. Definitely, I think you have an idea of this Dirac delta function. But for simplicity or for your convenience, I have mentioned here some of the important properties, or you can say the basic definition of this Dirac delta function. Actually, if you want to define the Dirac delta function, you have to state the following three statements. Actually, these three statements complete the definition of Dirac delta function. Okay. And what are those statements? This Dirac delta function, you know, is denoted by this symbol delta, and this is defined as delta r minus r naught is equal to 0 for r not equal to r naught. Okay. But this delta r minus r naught is infinity for r equal to r naught. And when you will integrate this delta function with respect to the volume for all space, the result will be 1. Okay. And for a finite volume V, this integral is again 1 if this V contains this R naught. Okay. But if R naught is not contained within this volume, then this integral is 0. Okay. Actually, if you talk about the one-dimensional, this is three-dimensional delta function, but if you are talking about the one-dimensional delta function, considering the volume value of x on this and Dirac delta function delta x minus x naught on this, and here x is equal to x naught. And you can see at x equal to x naught there is a high peak delta function infinity, and suddenly it falls to 0 in both sides when x is greater than x naught and x is less than x naught. Then abruptly this function falls to 0. Okay. This is the basic meaning of this delta function. Now you can see how in terms of this delta function we can define the volume charge density of a point charge. Okay. So for this, let us consider there is a point charge Q placed at a point P whose position vector is equal to R naught. Since this is a single point charge, so in this region there is no other charge present. Only at this point P there is a point charge, but all the other points are empty from the charge. Okay. Since at r equal to r naught there is a charge Q, so if you define the volume charge density rho at r, that will be defined by charge divided by volume. What will be that? If r is not equal to r naught, I have written at the points other than r equal to r naught. So this is the definition of rho for the point r not equal to r naught. You know, at the points where r is not equal to r naught, then there is no charge. So at the place of charge we will write 0 and volume is non-zero. Okay. And so the result will be 0. So according to this definition, except point r equal to r naught, or at all other points the volume charge density is 0. But now think about the point r equal to r naught. When you say at r equal to r naught, you have a finite charge Q. Okay. Thus you have a finite charge in 0 volume. When you say zero volume, it means you are talking like a mathematician and not like a physicist, because according to physicists the volume of a point is not exactly zero. It tends to zero but not exactly zero. But like a mathematician, you simply say that volume occupied by this point charge is zero. So at r equal to r naught, the volume charge density will be equal to q divided by zero, which is infinity. That is, we cannot define the volume charge density of this point charge at its location. Okay. So you can again, you if you integrate this volume charge density with respect to volume for all space, then result will be definitely q. Why it will be q? Because you know, in this region, in this whole region, there is only one charge q. So the total charge inside this all space is equal to q. Now let us see. All these properties are just equivalent to the properties of this delta function. You can see when r is not equal to r naught, then delta function is 0, and you can see this rho is also 0. And at r equal to r naught, you can see this delta function is infinity, and this rho is also infinity. And the integral of this delta function for all space is 1, and this will be also 1, because you can write it as 1 over q integral over all space rho of r dv is equal to 1. Okay. So all these properties of rho of r resembles with the property of delta function. Okay. But you have seen that for all space the integral of delta r minus r naught dv is equal to 1. So you can equate these two equations. So comparing these two equations, you can say that 1 over q rho of r will be equal to delta of r minus r naught. And therefore rho of r is equal to what? This is q times this Dirac delta function. So in this way, you can see how this volume charge density can be defined for a point charge q in terms of the Dirac delta function. So if you want to define the volume charge density due to a point charge q, what you will do? You have to multiply this q by the delta function, and that product will give the volume charge density due to the point charge. Okay. And if you want to write this expression in Cartesian coordinates, you can write that this rho of xyz is equal to q times delta of x minus x naught times delta of y minus y naught times delta of z minus z naught. So a point charge in this way, you can say, can be written as a volume charge distribution with volume charge density in terms of the delta function. Okay. So I think now it is clear to you how this delta function helps you to express the volume charge density due to a point charge. Okay. I think everything have been clear to you. Okay. Thank you very much.